Hi, y'all. It's Mrs. Blasky. Um, Today we're going to talk about topics 5.4 and 5.5. Topic 5.4 is about collision theory. This is probably one of the most common sense sections of anything in chemistry. Collision theory states that in order to react, molecules need to collide with each other, which makes sense. Two different parts of collision theory. Not only do they need to collide, they need to collide, number one, with enough energy to react with each other, and number two, in the right orientation um, in order to react. So we can talk about multiple things that increase the likelihood of those happening. So one thing is increasing the concentration. If you increase the concentration, you're going to increase the number of particles that are around to be able to collide. So that's going to increase your rate of your reaction. Increasing the temperature is going to do the same thing. It's causing those particles to move faster, which means that those collisions are either going to happen more often or they're going to happen with enough energy in order to make that reaction happen. So that also will increase the rate of the reaction. Anything that changes those two things are going to change the rate. We, way back when we talked about gases, we used this thing called Maxwell-Boltzmann distribution to talk about how the motion of the particles changed when we changed the temperature. And so in this first graph on the left-hand side, I'm going to zoom in a little bit. If we have a lower temperature, we have a lower average kinetic energy where that peak is, and we have more particles down at this low end of the kinetic energy. When we increase our temperature, remember this is that graph where we think of that line like a string, so we can increase how far down that graph goes, but as we increase that maximum amount of kinetic energy, that means our peak is going to have to come down. So we have less particles at that average kinetic energy, but we have increased the number of particles that have a higher kinetic energy. So we can talk about the same thing, talking about the number of particles that have enough energy to be able to cause this reaction to happen. And so we call that amount of energy we need to make the reaction happen, that amount of energy where those molecules need to collide with each other, we call that our activation energy. So we'll see another way to graph that in just a second, but basically the higher our temperature gets, the more particles we get above that activation energy, meaning that more particles are going to be able to react, our reaction rate is going to go faster. So we got some example problems. We'll do some of those in class. Topic 5.5 talks more about this amount of energy needed to make this reaction go. So we talked about activation energy. That is the amount of energy needed for this reaction to happen. You can almost think about it, and I like the way we graph these, you can almost think about it like a hill. If you think about riding a bike or a skateboard up a hill, you need to put in a whole bunch of energy to get to the top of that hill before you can then coast back down the other side of the hill. So that energy that you're putting in to get to the top of the hill is called your activation energy. We then would release some of that energy back out into the world by coasting back down the other side of that hill. We can see a difference here in the different types of graphs depending on the energy of our reaction. For an endothermic reaction, we put in a whole bunch of activation energy. When we come back down that hill, we don't go all the way back down to where we started. Some of that energy had to get absorbed in order to make that reaction happen. So that is an endothermic reaction. That means the energy has to go in to make that reaction happen. An exothermic reaction means we put in a certain amount of activation energy. As we coast back down that hill, we end up lower than where we started, which means we've actually gotten more energy out than what we put in. So that is exothermic, meaning some energy has been released or has exited from that system. In order to make this happen, those particles need to collide with enough energy to exceed that activation energy. Just for a split second, right when we get to that top of the hill, those molecules sort of form this big mash where we don't really have the same bonds as our reactants. We don't really have the same bonds as our products, but we call it an activated complex or a transition state. So that's sort of this in-between step of this reaction happening. Sometimes other chemicals get formed there. Sometimes it's just a big mess of bonds and things rearranging. It sort of depends on what the reaction is looking like. So we should be able to identify what is the activation energy, whether energy has been absorbed or energy has been released, based on looking at these energy diagrams. Sometimes we have steps or we have reactions that take more than one step to accomplish. We're going to talk about that in section 5.6, but just to sort of give you an idea, this is what the potential energy diagrams would look like for something that has more than one step. Each step of that reaction is going to have a different amount of activation energy that is needed. But what we call the overall activation energy is the amount of energy needed to go from our reactants to the highest peak for that entire reaction. So for in this first graph, our highest peak is our first step of our reaction. So that's where we have to put in the most energy to get up that hill. After that, we're going to be able to coast almost like a roller coaster down all those other hills because we're never having to reach that highest peak again. In the second graph, our highest peak, the most amount of energy required is actually in our third step. So again, if you think about this, we're going to have to put in some energy to get up here, then we'll get a little bit back out. And then we put in a little bit more, and then we get some back out. But then we really have to put in energy to be able to reach that highest peak because we have not gotten up that high yet in terms of energy. If you're looking up information about this on other sites or in your textbook, they might talk about this thing called the Arrhenius equation. Excuse me. It has a mathematical relationship about activation energy and temperature and all sorts of things like that. That is not going to be tested on the AP exam. It's basically just sort of a plug and chug equation. It doesn't tell you a whole heck of a lot. So we don't need to worry about that. The last thing that we need to talk about how it can change a reaction is a catalyst. So a catalyst is a substance that we add to a reaction that changes its rate, but the catalyst itself does not get consumed in the reaction. So it doesn't act like a reactant. It doesn't automatically change into a product. It stays there or it gets reformed again and is unchanged. Catalysts always make things go faster by reducing the amount of activation energy needed for the system. So here we've got a graph. This pink purple line shows a normal energy diagram for a reaction. By adding in a catalyst, we can see that this activation energy, the height of that hill, has been lowered. We still are starting at the same energy for our reactants. We're still ending at the same energy for our products, but the height of that hill, that activation energy has been decreased. Lots of times that activation energy gets changed by providing a different pathway, by providing those molecules a different way to rearrange themselves into the products. And that different way of rearranging requires less energy. And so that's how we get catalysts to function. Catalysts are a really important part of life in general. There's tons of biological catalysts going on in your body right now. Lots of enzymes exist as catalysts. There's a thing in your car called a catalytic converter that helps decrease the amount of smog your car makes, all kinds of other things. And so we will be talking a lot more about catalysts when we start talking about the steps that reactions can take in section 5.6. So hopefully that helped you out. I will talk to you later. Bye, y'all.